this CODSCOMAD 2019 conference. So this is specifically meant for the young researchers. So as you all know that requirement was that the first author of the paper should be either a PhD student or just has completed PhD in the last couple of years. So we received quite a number of submissions, more than what we had expected. There were 62 submissions. And so after the reviewing process, 28 were accepted. And I must say that several reviewers later told, okay, so sorry, I should have introduced myself. So I am Saptarshi Ghosh, and Soheli Bhadra here and we are chairing the YRS session. So welcome to all of you. So as I was just saying, we had a reviewing process where at least two members of the program committee reviewed every paper. And several of the PC members told me later that the standard of the presentation or papers were quite high, much more than what they had expected. So thanks to all of you who have submitted papers, and congratulations again for those who have got their papers accepted. Now, out of the 28 accepted papers, they will be presented over the 3 days of the conference. So today there are 9 presentations. So now we are running under a very strict time schedule. So we have exactly 90 minutes for the 9 papers. So 10 minutes for each paper. You have 8 minutes of talk and 2 minutes are kept for question answering. So when you after you have started your talk, after 5 minutes, you will be given a signal by Soheli that 5 minutes are over. Now you have just 3 minutes. Okay, sorry. When you have 2 minutes left, that means after 6 minutes, you will be given a signal that 2 minutes are left. And after 2 minutes, you should actually stop your talk, because the next signal would be stop, and please take that as a hard signal that you have to stop your talk. So please adjust your talk accordingly. And then couple of minutes are kept for question answering. Maybe we can have 1 or 2 questions in every poster, right? So any questions from the ones who are presenting? So you know the schedule of your presentation. As one speaker is about to finish, I would request the next speaker to be ready. Maybe you can actually come up here and wait, so that immediately later you can start. Okay. And for all of you, the posters would be displayed today 6 to 8 p.m. and make sure that you put up the posters between 5:30 and 6. Okay. So please be sure to put up your posters, and you have a designated board where you should put up your poster. That mapping would be available. Please check that mapping and put up your poster on that board which is designated to you. Fine. So I now hand it over to Professor Shorangshu Bhattacharya, who will be the session chair for today.
Okay, so without wasting further time, let me invite Aryam Das, who is going to talk on a poker-styled on-device selective privacy preserving framework for recommender systems.
Hello everyone. So I'm going to present our ongoing research about poker-styled selective privacy preserving framework. So just a brief overview. So in recommender systems, we are basically trying to find the missing entries in a rating matrix, and one very popular technique is collaborative filtering, which is based on the intuition of homophily that similar-minded users will likely like and rate items accordingly. And one very common way to solve this problem is through matrix factorization, where you calculate the incomplete ratings matrix as a dot product between user latent vectors and item latent vectors, where we solve this loss function and calculate this. There is an inherent conflict in this, that the user needs to explicitly rate some items. So the more the ratings he or she gives, the better the rating prediction accuracy. But there is this also leads to some privacy concerns, because there are some items which a user does not want to rate, maybe because of these items could be on politics, religion, and hence they refrain from rating these items, thus the accuracy of the model goes down. So in the current literature, if we look at this, there are 2 ways to solve this. One is peer-to-peer based techniques, where where the authors suggest that if you do not trust a central recommender system, have a trusted peer network where each peer share the ratings, and then you can have a more or less average recommendation. Because but not all data is pooled together, this recommendation is not that accurate. And also this does not scale because the trusted peers do not scale beyond a certain limit. The other is through differential privacy-based approach where each user masks its rating value through some noise and then uploads it to the central server. In our experimentations, we found that this, though has the privacy guarantees, the actual performance is much worse than just having a few ratings. What we propose is that let each user define his or her own privacy policy. Since each user's privacy definition is different, let each user define it. How does a user define it? We have an option of giving the user a rating, and if the user wants, it can be shared publicly and uploaded to the central recommender systems. Otherwise, it can be stored privately on the user device. This is similar to a poker game where you are given cards. Some of them are visible to the players, and some is privately dealt to you, and you have to form the best combination. So we took a user survey to find out how many people are interested in this system, and in a small scale survey of 74 respondents, we found that almost only 10% people regularly rate, and half of them have, majority have concerns about privacy issues. And we found that a significant of them, over 50%, would likely adopt this kind of system where they are guaranteed that the performance will improve if they rate privately on their device. So how does this system work? Well, this has a few steps. So the first step is that the users rate their items publicly and then upload to a central recommender system. Second is the user then downloads the corresponding public user factor. So each user has their own user factor, and they download just their corresponding one. Along with this, they also download some auxiliary model information. This is common, and this can be downloaded by all the users. Okay, this is the same one that is downloaded on each device. And then we have performed some local updates based on this auxiliary model information and each user's private ratings. So through these local updates, we get the private user factor and the private model, which is then stored on the user device, and these are never shared. So this private model, which the user calculates on device based on the private ratings and this the public user factor and the auxiliary model information downloaded, is used to give the final recommendations. So we tried with different implementation strategies. We basically tried 3 ones. First one was a naive implementation where we tried downloading all the item factors. So this gave us the best accuracy, but this required significant on-device storage and was also required huge amount of download size. And this was not scalable as the number of items grow. So we tried a next clustering-based approach where instead of downloading all the item factors, we downloaded just a few representative ones, much smaller in number. So this one had relatively lower accuracy, but this required less storage and download cost. The third one, we actually downloaded a compressed approximate item factors. We downloaded all the item factors, but they were much compressed and approximate. So this yielded similar performance to naive implementation, and it required less storage and download cost. So another thing we looked in was, in our experimentations, is how should we divide the private data? So because this is hard to mimic a real life situation in this, so we came up with 2 hypotheses. One, where each user independently decides which item should be rated privately and publicly, and the second, where users do not decide independently, rather some items are more likely to be rated independent than others. So based on this, we came up with 2 ratios. One is user privacy ratio, which just decides how many of the ratings should be marked, user marks private, and an item which tells how many times this item has been marked private. And we chose 4 beta distributions. One is mostly balanced, mostly extreme, most pessimistic, and most optimistic. Just this actually mimics the privacy ratios across a population. And we had some baselines of absolute pessimistic and optimistic, which means that a user does not share anything or a user shares everything. So what we found is that first benchmarks that in a normally the privacy preserving methods do not perform well In fact, between the absolute pessimistic and absolute optimistic, which is the theoretical upper bound, there is only 7% gap, and the only public comes in between. If the user just do not rate anything and only uploads the ones he's comfortable with, which is only public, it comes in between these two bounds, and our performance improves upon only public. The performance improvement varies across the distributions, but it is significant in the sense that 1 or 2% in recommendation system is huge, as we see that the gap between absolute pessimistic and absolute optimistic is just 7%. So there is a common pattern across all of these, which is that the naive performs better than joint optimization, better than clustering, and all three better than only public. The improvement degree changes according to how much privacy ratio is, what is the privacy ratio, average privacy ratio in the population. And this is the size-wise, we look at the naive takes a lot more, requires a lot more download compared to joint optimization, which is an order of magnitude, requires an order of magnitude less the data. So just to summarize, we discussed this privacy preserving framework, which allows users to have their own individual privacy policies, and we proposed 3 different strategies to ensure scalability. We also conducted a user study that shows that a majority of participants are interested in this kind of framework. So I would acknowledge my advisors, and we have our full paper which we have the details of the strategies and the designs. Thank you.
Manage the security of the communication channel using which the ratings are being floated or ratings are moving from one into another. That means from private to the public domain.
So you can have a security key based, and so there are 2 kinds of information that flows. One is the user factor, which could be encrypted between the server and the device and the user, and another is the auxiliary model information, which can be bulk download, which could be like an update, like an OS software update, which could be available to all devices. That needs to not be encrypted. So yeah.
Okay, so every user needs to share a private public key pair with the server in order to communicate. Okay.
Yeah. So we had 2 assumptions, which I skipped. One is that the very practical assumptions that the central recommender system is not malicious in nature. That is because it is there against their interest to hijack any kind of information, because then their recommendations go down. And the other one is that, but they would try to be, they would want to get more information that hampers the user's privacy without hampering their recommendations.
Abhishek is going to talk on CNN-based context-sensitive lemmatization.
Good morning, everybody. I am Abhishek. The topic of my presentation is CNN-based context-sensitive lemmatization. So lemmatization is a task in natural language processing, and before going into the details of it, I would like to say the background of this work, why I have done this. So major Indic languages, for example, Bengali, Hindi, Marathi, so they suffer from high level of inflections. That is, for a particular root word, there exist variants of it. So lemmatization is a foremost task in morphological analysis. So what it does, it returns the root form of a word in context. For example, in Hindi, for the surface word agle, the lemma is agla, that is the root form. For chunabo, the word is chunab. For unhone, the lemma is wo, and so on. So in various semantic processing tasks, for example, word sense disambiguation, similar sentence finding, the lemma is required. Why it is required? Because when we face a surface word, so if we want to know its meaning, then we have to get its root word to search in the dictionary. So lemmatizer does the same thing. It maps a surface word to its root word in the dictionary so that we can get the semantic information about it. So challenges in doing the automatic lemmatization task. So first thing is variety of edit operations required. For example, the surface word can be generated from the lemma by addition, subtraction and replacement. So here for the surface word lagai, it is obtained by addition of a valid suffix e to its root laga. For this surface word ho, it is obtained using the subtraction operation from its root. And for the word agle, it's required a replacement operation from its lemma. So the second challenge is presence of irregular word forms. For example, gaya to ja. So here no specific addition, replacement or subtraction operation is not required. And the third challenge is context sensitiveness. So Indic languages are very much context sensitive. For a particular word form, its lemma may get changed on varying context. For example, if we consider the word curd, so first sentence is jal kar dena hoga. In this sentence, its lemma is curd itself, that is in the meaning of tax. And the second sentence is mera kaam kar do. In this sentence, the lemma of curd is karna, that is in doing sense. So these are the basically the challenges of doing automatic lemmatization. So first thing is word lemma transformation pattern. It is to note that the word lemma transformation pattern is represented by a tree called edit tree, and the edit tree embeds all necessary edit operations and it is generalizable. For example, for the word walking to walk, the edit tree is this. So if we apply this tree to walking, it gives the lemma walk. So how? So that is in the root node of this tree, the prefix length is 0, suffix length is 3. So if we subtract the length 3 suffix from it, so it gets ing, and the right branch of this tree, it gives ing to null. So this tree gives walking to walk, and the same tree is applied for the word going to go, reading to read, and dozen, and so on. So my methodology is that I have proposed a supervised and contextual neural lemmatizer. So unique edit trees from training data gives the class labels. That is, we have a training data where the words are tagged with their gold lemmas, and first we have extracted all the unique edit trees from the data. So these unique edit trees basically refer to the class labels. And our proposed lemmatizer classifies appropriate edit trees for sentential words, and our method is independent of manually defined features. So this is the model overview. So our model is a composite deep structure. Here the sentential words are fed through the model, and there is a shared BLSTM which character level encodes all the words. That is, it first defines a character level embedding of the words, and then this character level embedding is fed through another CNN model which finally captures the context and predicts the appropriate edit trees. So how the character level embedding is done? The character sequence of the words are first fed through an embedding layer, and from the embedding layer the outputs are then fed to a BLSTM model. That is, there is a forward LSTM and there is a backward LSTM, and the final output of these two LSTMs are joined to make the character level embedding of the words. And finally, the next level CNN does the edit tree classification. That is, the first character level embedding of the sentential words are fed through CNN, and CNN generates the positional embedding. That is here the Q1 to Qn, and here one thing is to note that the size of each filter in CNN is basically 2c plus 1 into d, where d is the size of E1 to En, that is the character level embedding size, and c is the context length, which is a hyperparameter in this model. So context length, so 2c means that is the left context length is c and the right context length is also c, and 1 is for the focus word itself. And basically it generates the positional embedding for each word. And finally, so it does the edit tree classification. So let the set T1 to Tk be the set of distinct edit trees in the training set. We find an applicable edit tree vector of each word from the training set. That is, all edit trees in the training set are not applicable to a particular word. Some trees are not applicable at all, which we know at prior. So finally we combine the applicable edit tree vectors with the positional embedding, and we pass through it a dense layer, and then we apply a softmax layer to get the final edit tree classification. So our experiments, so we have selected 2 Indic, Hindi and Marathi, and 2 European, French and Spanish languages for experimentation, and the universal dependencies tree bank data are used. So BLSTM CNN is our proposed model, and we compared our results with the BLSTM model and the lemming. So these two baselines are used in our experiments. So lemming is a CRF based lemmatizer. It designs the handcrafted features, and BLSTM model is it captures the full context, whereas our CNN model it captures the local context. So for 3 out of the 4 languages, our method it gives the best performance, and for Spanish the CRF based lemmatizer it gives the best. So from the result it is proved that if we do very much of feature engineering for a particular language, then it can beat the deep learning based approach. So finally, so we experimented with different context length of CNN. So we see that when we use only character level embedding, then at context length 1, that is we are taking only the left and right adjacent word of the focus word, it gives the best performance. So and the accuracy monotonically decreases when we increase the context length. So thank you.
So one question is why like you are using CNN in the input layer and not LSTM?
Okay.
In the output layer and not LSTM, and input layer why are you using IRN or LSTM and not CNN?
Okay. So for doing character level embedding, we have to consider the whole character sequence length of a particular word. Right. So that's why I have used LSTM. It captures the full character level sequence. Okay. But for the final edit tree classification, the whole sentence length is not needed to classify the edit trees. That's why I have used CNN, where it captures the local context and it is kept as a hyperparameter.
I think you can capture the local context by using shorter length LSTM or LSTM also, right?
But yeah, shorter length LSTM may be used, but that does not capture the full context. Okay.
Okay, any other question?
Just a quick question. For different languages, it seems to work nicely, right? Why do you think it's possible like that? And you have tested with 4. So if I test with another 40, do you expect to get similar results?
So if we restrict on only character level embedding, then the experiment results suggest that using a considering only a local context would be beneficial. That may be done using CNN, or any shorter length LSTM can also be used.
So to capture the character embeddings, so have you tried using the CNN for capturing the character level embeddings also, because they may be helpful in extracting the vector representation?
No, I used LSTM for this purpose because to encode the character level representation of words, considering the full character sequence length is very important. So here the ordering of between characters is very important. So that's why I have used LSTM.
So can you go back to the previous plot on the context when?
Okay. Yes.
Yeah, the context length. So it seems like 1 is giving you the best performance.
Yes.
What happens if you just go to 0?
So
I mean, is it important at all? That's the, I mean, as you increase the length, it's sort of going down.
Okay, that depends on the data set. Okay, so if in the data set the contextual dependency of words is not very much, then I think just without doing any kind of deep structure, just a dense layer would be sufficient to classify the trees. But where the context is very much important, so there considering a local context is, I think, very beneficial.
Right, but do you have any data or experiments
No,
on this?
sorry, I did not use that. That is keeping context length 0, I did not use that experiment.
Okay, thank you.
Okay, so in the interest of time, we will not take any more questions. So you can talk to the speaker offline. Swapnil Gandhi. Yeah, please come. So Swapnil Gandhi will talk about from think like a vertex to think like an interval.
Not completely evident from the title, my talk is going to be about large-scale temporal graph processing in distributed systems. This work is in collaboration with my research advisor, who is Professor Yogesh Simon at Indian Institute of Science. So what are temporal graphs? Temporal graphs are actually dynamic networks which vary essentially evolve or shrink with time. As a matter of fact, all of us are living inside a temporal graph. Examples being Facebook, Google Maps, and things which vary with time, right? So before even I move over to the challenges, I want to discuss why even scaling is something which is necessary, right? So taking a step back and moving over to static graphs, which is considered to be the gold standard for big data workloads for the last decade or so, we see that there are only a handful of companies like the Facebooks and the Googles of the world who have the coveted trillion edge graph, which requires scaling, right? And now moving over to the context of temporal graphs, I like to call them long data. So even if you have a very small topology, right, if you want to perform your analysis over a long period of time, the graph can simply run into billions of edges, and that necessitates the need for scaling, right? So those are the key points to highlight. Next, the challenges in the current state of the art, right? So the challenges are that there does not exist a unifying abstraction. The abstraction itself only works for a subclass of problems, right? And the second is they're not designed for scaling. So our work is the first scalable and distributed system for processing temporal graphs in general, right? So to concretize your understanding of a temporal graph, here is an example. So the top part of the slide shows you red, green, blue, and orange. These are 4 vertices. Think of them as users of Twitter, and the arcs are actually showing you the follows relationship. As it happens in the real world, users follow and unfollow people. That is captured via the time interval that is shown on the edges or the arcs that you see. Now, we could do a variety of analysis on top of this very simple graph, but to keep things simple, we are only interested in seeing the evolution of your followers as time progresses. The expected output is shown at the bottom of the slide. Now, what we are going to do is we are going to discuss first what interval-centric computation or thinking like an interval is, and then we are going to fill in the details. So what are we doing here, right? So there is a very famous almost a decade-old Google paper which argues that you should think like a vertex. What we do is we extend the think like a vertex concept, and we introduce think like an interval concept, wherein users using our simple API write an interval program, and as part of the API we expose interval as a first-class citizen. Right? Our model is based on Valiant's bulk synchronous parallel model, thereby every communication only happens via message passing, and at the end of each iteration you have a global superstep, and then the computation progresses in multiple iterations known as supersteps. Right? Our API, though simple enough, is flexible to express a variety of algorithms, and we actually take 10 different algorithms from literature which are covering about 10 years of work and represent them in our system. Right? So the lifespan of an interval program can be explained in as an interval state machine. So here what happens is you have an interval which is active, it does some form of computation, and it always at the end of the iteration goes into a sleep state. If it receives new messages, it reactivates, and the computation progresses. When all the intervals are deactivated, your computation halts. So revisiting the toy example, what do we do here? In super step 1, we initialize the followers count to 0 for everybody. Now what people do, now what you do as part of an interval is you send an interval message to your neighbors, right? Everybody contributes value 1, and thereby you have messages flowing across the network with some time intervals. So those are shown in the figure. In super step 2, you accumulate the results, you do some computation, in this case it is just summing up, and you finally have an answer. This is a simple example, that's the reason why you have just 2 super steps. In reality, it could run for multiple tens or hundreds of super steps. So I skipped on a very simple part. So how do we accumulate stuff? So for that we have something called as warp. Warp is not novel. It has been in active research in database community for over 2 decades. The way we use it is interesting. We are the first people to use it in context of temporal graph processing, right? And it gives us very nice formal properties. So what we can do here is we can minimize the number of compute, thereby reducing the wasted computation, and we can also reduce the messages that are flowing over network. More details are in the poster. I encourage you to talk to me offline, right? And as I'll show you in the next slide, this leads to significant performance improvement. So we have 2 distributed baselines. Both of them were proposed in PVLDB 2014 and 2017. And again, due to lack of time, I'll not go in depth into them. So how is the performance evaluation? Over here on the y-axis, we have runtime in seconds. On the x-axis, we have 5 representative algorithms. The analysis is being run on a graph with cumulative 5 billion edges, and the largest snapshot has a 1 billion edge. All of this is running over 8 commodity machines, and it is supported by gigabit Ethernet. So what do you see here is, we see that ICM outperforms both the baselines by a factor of 3 to 9, right, across the general class of algorithms. And again, the numbers are there. I can talk about them in depth during the poster session. But what I want to highlight is that is what makes ICM fast. So we see 2 side effects or 2 primary effects of warp. One, we actually reduce the number of compute calls from 63 million to just 14 million in case of ICM. That essentially helps us reduce the wasted computation, plus the number of messages that are being sent out over the network are actually 6x less. In the real world where you are sharing the cluster, this will lead to significant better utilization of the cluster itself, and this is a property that is desired. So in summary, I introduced what temporal graphs are. The applications of temporal graph are in various domains, running from social networks, medicine to biology. I briefly introduced our scalable and distributed abstraction for temporal graph processing. The API is simple enough. The code, we are trying to iron it out and push it into open source. It's built on top of Apache Giraffe, which is maintained by Facebook. And I also showed how ICM currently outperforms both the distributed state-of-the-art baselines, and our ongoing work is actually currently trying to support or add support for real-time streaming updates. So instead of just doing computation on historical data, you can process real-time data as well, and on effects of graph partitioning. Thank you.
What kind of queries you use to test the performance?
Yes. So we have, actually we don't have queries, we have applications. So one of them is temporal breadth first search. The other is single source shortest travel time. The other is latest departure, fastest arrival time, and time minimized minimum spanning tree. So all of these are considered to be representative algorithms, on top of which you can build elaborate systems.
So these are all recursive queries, right? I mean, the single source shortest.
Yes.
So
yes.
The systems like Giraffe or other, I don't know the ones you compared with, they're not known for perform that well on this kind of recursive queries. So have you looked into systems like Big Data Logger that is meant for this kind of recursive tasks?
Correct. So actually our system is built on top of Giraffe, but instead of going after a declarative querying system, which is where the recursion does not work well, we actually go for an imperative style of programming, wherein instead of recursion, you can think of it as multiple iterations. And the user is more in control of how he can control the iterations itself. But I can definitely talk about it more offline.
So that was a nice talk. Can you share some details about the consistency? Does your model follow eventual consistency? How much is the consistency delay?
Sure. So our model is actually synchronous. So the model actually gives you exact answers, and the computation actually runs in iterations. So after every iterations, you will have a global barrier. The global barrier will ensure that both the super steps are synchronous. So it would be synchronous, or the strongest form of synchronicity is serializability. So it would be that.
Okay, other questions?
Yes, I wanted to know on what graph this performance has been evaluated.
Right.
And
So,
what was the
this is
scale?
this is actually a Twitter graph. So we have taken 10 snapshots, and the largest snapshot had upwards of just about 1 billion edges, and cumulatively we had about 5 billion edges.